We're trying to figure out how accurate we could expect our approximation to be if we were to use this polynomial to approximate e to the 1.3. You recognize this as the third order Taylor polynomial for e to the x with 1.3 plugged in for x. We also know that we're going to want to use parts of what would be used to create the next term of the Taylor series. So the fourth order term, which is the fourth derivative of the function that you're approximating, x to the fourth over 4 factorial. Of course, the fourth derivative of e to the x is still e to the x, and now here's where all the discussion has to happen. We need to figure out an upper bound for e to the x that makes sense, and an upper bound for this. Things that are definitely bigger than the error, but not so big that they become useless. Looking at this e to the x, let's talk about that. I want an upper bound on that that's definitely going to be larger than any value between the center of the series, which is at 0, and any relevant x values. Now in this case, the relevant x value is 1.3. So if I want to make this as big as possible, but still not too crazy big, I can just use e to the 1.3 because that'll be larger than any x's between e to the 0 and e to the 1.3. But it won't be so big it'll be crazy. Of course, we don't really know what e is, otherwise we wouldn't be doing this necessarily, so instead of using e, I might use 2.8. So I would probably replace e to the x with 2.8 to the 1.3. Now for the next part, I want to find this is an x value, and we know that the Taylor polynomials are going to peel away from the actual function the further out you get. So we want to put in an x value that's far enough away from the center to be relevant. So in this case, like 1.3 is, I want to go out to at least 1.3 because I need to cover 1.3, but I don't want to go any further than that because then I'm going to be too far from the center. So basically, I'm going to let x equal 1.3 in this case because it's close enough to the center to be possible, like useful, but not so far away that it's crazy, giving me that value for x. So with that calculation in mind, putting that on my calculator, I get 0.453, and that means that the approximation that I get from this will be within 0.454 of the actual value of e to the 1.3.